Okay. Yes, good afternoon. Thanks for inviting me to give this talk. Actually, I'm not grateful because I had to remember things from many years ago, which I've already forgotten. But I hope I haven't forgotten everything. Well, I mean, I have forgotten a lot, but I hope I have managed to remember the essential things. So, well, I think this talk is perhaps an addendum to Leonard's talk last week, for those who were there. And let me start with the definition. So we need definition of polyhomogeneous functions, right? PHG functions. So I'm going to think of them as there are two ways of thinking about it: at near x equals 0, or near r equal infinity, where r is and then x is 1 over r in this definition. Okay, so if you know what a polyhomogeneous function near x equals 0 is, then you just take, and you're interested in expansions in 1 over r, just set x is equal 1 over r in the expansion. And so these are going to be functions which are asymptotic to, and there will be something called an index set, so maybe SI, J. So there will be some. The cleanest way to write it is probably smooth functions here, Sij. So x to Si log to Tj in a set. This is called an index set, right? So, and these are smooth functions up to. So you think of this as function defined for x, say larger than 0. Then this would be a smooth function on this set x larger equals 0, so up to boundary. You can think of this as you could take a Taylor expansion of this function if you wanted to, and only keep the part of f which depends on the boundary, but it's cleaner as far as coordinate transformations go to write something like that. So, okay, so let me just make sure that what we're talking about, right? So we have a manifold, we have x equals 0 is the boundary, and we want, I like to think as x being positive on this side, which is weird, but makes sense if you think of this as 1 r going to infinity, right? So you have functions defined on this set. So x is this variable of this boundary, and you have variables on the boundary, and you could just say that these functions are functions on the boundary, but it's, as I said, nicer to think of them as being functions defined everywhere, and not say that these are functions on the boundary. Okay, yeah. So this is right. So probably what you want is SIs to be positive. No, anything. They could be integers, half integers, whatever. Just any sequence, right? Yeah. But not even you want no. Yeah, you want them to go to infinity. I'm going to assume that they're real. You could even do this with complex things, but then, well, this still makes sense, but there'll be oscillating terms, which I don't want to think about it, right? So for me, this exponent will be real, and I think that so I is a subset of R square, right? And probably what you want is that for each I, there's a finite number of non-zero. There's a finite number of TJs, right? For every I, finite number. So that's sorry, what is SI? SI goes to infinity, right? Okay. Yeah. Okay, so an example would be and usually one often asks that you want this maybe this, if you want this function to be bounded, so maybe you want this. So let's assume that if S0, right? So S0, so if Si equals 0, then all the Tj's are 0, right? So in other words, the leading order term is bounded, right? You don't want to have, for example, if this is 0, you could have logarithms here, then they would be going up, right? So if I is 0, then there are no Tj's, right? So in other words, so think of a function which is f is asymptotic to a function of f0, 0 well, actually a smooth function plus, I don't know, f0, 1, x to some x1, 1 log 25, right, plus things like that. Okay, there could be, there's at each power here, there is a, you could take, let's think of this sequence maybe as increasing. Okay, SEI plus 1 larger as I. Okay. So that's an index set, and in the context of that we're thinking about in this gravitational field, then we'll be looking at expansions like the metric will be r square time a metric which depends upon the angles plus maybe 1 over r some first correction which depends upon the angles plus maybe there could be a log r over r g, so this would be 1 and 1 because there's 1 and so forth, right? So that's the kind of expansion that you've seen here. Right, exactly. And what does this series mean, right? So this means that if you take any number of derivatives, and an elegant way of differentiating partial powers, because this could be non-integer powers, right? So if you like to differentiate using x dx rather than dx, because if you take a x 1/2 and you use x dx on it, you're going to get probably 1/2 x 1/2. So you reproduce the power up to a coefficient, right? So, well, if you differentiate it only with dx, you'll be losing powers, right? So, I mean, it's going to be, if I differentiate that, I'm going to get a negative power here. There's nothing wrong with that, but I mean, it's easier to formulate the concept using this derivatives. So if you take any number of derivatives x dx to any power, and let me call this coordinates ya. So does any coordinates, so dy1, j1, dy, because you had dimension n. So so this is y1 yn minus 1, yn minus 1, jn minus 1. You take this function, you remove a finite sum, so not the whole sum, but you remove a finite part of the sum, right? So minus this sum up to some finite number. So there exists a finite number, so this is, say, well, what would you assume that this decay is smaller? Okay, this is smaller than x to n, okay? So for any n, so the statement would be, so that for every n, and then for every set like that, every I and so forth, G1, Gn, there exists a constant C and a finite sum here, and a finite sum. Maybe I should write it finite sum like that one, finite sum. After you remove the finite number of terms, you have something which decays as fast as you wish, right? And so that's polyhomogeneous. Yeah, right, yeah. So that's probably a normal regularity or something like that. But so keep in mind that if we're thinking about Einstein equations, that in even space-time dimension, this works very well in the theorems I'm going to tell you, where these are integers, and these log terms start at some maybe far in the series, not immediately. Right? So maybe there's a few terms here without log terms. And that if you are in a odd space-time dimensions, you need half integers here. They work very well. But you could be in even dimensions, put half integers in your initial data. Nobody prevents you doing this. And then you're going to get a solution, which these things are all preserved by the dynamics by suitable theorems. So that's the setup. Then the first key theorem is the following. So this is a meta theorem, which is essentially due to Vaschi and Hinz, or Hinz and Vaschi. So this is Einstein equations, vacuum, and in dimension, well, in any dimensions, but lambda equals 0, any dim. And let me just draw the picture. So this would be t equals 0. This would be what we call usually I0. It's actually a boundary. There's a corner which is followed by what we usually call scri plus. So I'm doing this kind of symmetrically, but you just have to rotate it, right? So this is scri plus. There's another corner here, and this is something what we usually call I plus. And I'm not going to draw it symmetric, right? Symmetric. Oh, let me just draw this symmetric. Good. And the meta theorem is that so for any dimensions, then polyhomogeneity is preserved by evolution. And what do I mean by polyhomogeneity is preserved by evolution? You take homogeneous, so locally. So you take polyhomogeneous data here, they're going to stay polyhomogeneous for as long as they exist. And for small data, but it's much more, because it's telling you, well, you can take this data at t equals 0, but you could take characteristic data rather than, or you could do something like that. So data which are characteristic here and here, polyhomogeneous here. Polyhomogeneity is preserved for large data as long as the solution exists. And for small data, you get global solutions. I'll comment more about this theorem shortly. Well, it's always, these functions are always bounded, right? So if you think in terms of the metric, there's always be a leading part, which is well behaved, and that'll be correct. And these logs can jump in there somewhere. And right, and if you don't have logs here, doesn't mean that you will not get them here. Right? Or maybe you have logs here, they're going to vanish. Happen. This index set, you would attach a different one to every face, probably, right? Because they are physically different things, right? So this is so there'll be some index set here. But so you have a global. Well, since there's a finite number of index sets, you have one, right? So this means that you have a polyhomogeneous expansion in terms of at t equal constant, and we're going to infinity. If you started with such data, nobody forces you to have polyhomogeneous data. You can start with data which have a finite number of derivatives, and there are still theorems which work for this, right? So nobody says life has to be polyhomogeneous. You could stop this expansion at a finite point and get something in a weighted Sobolev space, right? So there are theorems like that, but I don't want to overcomplicate it, so let's just That's complicated enough. So yeah, I mean it's Lorentzian. It is Lorentzian. But in the Euclidean, the Cauchy problem is not the right thing to look at. Right? So there'll be other, but yeah, lambda equals 0 Euclidean. No idea. Lambda negative Euclidean, you have polyhomogeneity theorems as well. But, right. Yes? So small being, there is a weighted Sobolev norm here. I think Vashian tell you there exists a big N, and they saying N equal 24 is good enough. Right? But right, yeah, close to Minkowski. Small data means near Minkowski. Right. So a lot of people, including myself, have wasted a lot of time trying to understand which logs propagate, which don't. And Kerenberg was about it, right? So what can you say about existence of some log? So I'm going to write one of his theorems that he already mentioned last time, but just remind you. But let me just finish this picture, right? So first, you could have an expansion in terms of 1 over R. This is polyhomogeneous, right? So expansion in 1 over R, X is 1 over R, and all these powers are 0, right? So for every I, you have this, right? So SI would be just, right? Then you could have this, but nobody tells you that this is going to be smooth here. Right? So, and actually, you don't know that it's going to be smooth at this stage. And also, let me mention that also telling you that there is a polyhomogeneous expansion at I plus, right? So if you try to, at fixed, if you look at a fixed space point and expand in time, then the metric will also have this polyhomogeneous behavior. Good, so this is, and let me tell you why this is a meta theorem at this stage, but the other important theorem is essentially Covino and Schoen, or Covino, which says that if the data are stationary outside of a compact set, well, there exist data which are stationary. Okay, there exist data which are stationary outside of a compact set. So there exists a lot of data for which the metric is exactly stationary here. And then there is this fantastic theorem of Friedrich, which tells you that, well, such data have a smooth, well, such data have a smooth scri, data lead to a smooth scri. And global if the data are small, right? Global for small data. So global for small data is actually not Friedrich, but Christopher Kleinerman, but of course you could just invoke this theorem, right? So in this case, you get a smooth expansion here, you get a smooth expansion here. I'm not sure what's happening at these corners. So Heinz and Vashi is telling you that the corners you get a polyhomogeneous one, and I don't think anyone proved that it's going to be better than polyhomogeneous, but who cares? Here it's smooth, here it's smooth, here it's smooth, and there are some weird corners where it might not be. But if you look at null hypersurfaces, right, or if you're looking at or light rays, they all end up in scri plus. They don't meet this point, so they'll be. So it's only very funny curves we got here, curves that nobody cares about. I've never heard anyone being interested exactly in these curves, except people trying to prove smoothness, right? And then you have to worry about this. But physically, nobody's been interested in what happens with the metric in this region. So here, for this data, if the data, so I want to look at this following way, right? It's something non-trivial happening here, but here you have curve or Schwarzschild or any stationary solution. There's a lot of them, right? So stationary globally regular, we think curve. But if you think stationary outside of compact set, they're characterized by an infinite number of multiples. So there's a lot of solutions here, like that. So for these solutions, you're going to get a smooth scri plus, smooth developments here. Everything will be smooth if they exist globally, and if they and locally, they will certainly have a small piece of scri. Now, why is this a meta theorem? Because first, Hinz and Vashi explicitly assume 3 plus 1, but everyone in the field knows that anything larger than 3 is easier. Right? So you can do it in 3 is a master thesis exercise for a good student. So 3 is, you can forget it. Then they set it up globally, right? So the theorem is stated as small data, while I'm saying this is true and this is clear for the method. So in other words, if you have polyhomogeneous data which are large here, you're going to get a smooth, a little piece of space-time which is polyhomogeneous, and you can do it also start from scri minus, and then if you want to start to scri minus and evolve to the future, there is a catch because you have to say what the field is doing here. And this, I don't think anyone has written this down, but Leonard said last time that they wrote down this part of the proof with, I think, polyhomogeneous behavior here as well. Right? So if you're solving to the future from a say, hyperboloidal surface, then you need to give initial data here, but you also have to give the radiation field on this piece to be able to solve to the future, right? To the past, that's good enough. But if you want to go to the future, you need to give the data field. And Leonard wrote, well, mentioned last time that they can do this, this part. So as I said, the methods are clear, but you need to sit down and write it down, and so they did. Also, they assumed Schwarzschild plus corrections. And this part has not been written down by anyone. You could have a metric which goes to a flat one. That doesn't have to be Schwarzschild plus correction. The leading order doesn't have to be Schwarzschildian, right? So they're assuming that the metric. So if you look at this polyhomogeneous expansion of the metric, this would be the full, let's say, initial data. Then this would be these two terms would be exactly Schwarzschild, and the corrections will start here. Right? So that's what they did in the proof. Again, it's clear that it's not needed, right? So this is probably more than a master thesis, but it could be master. Yeah. So you could have a. They're assuming that these two things are Schwarzschild, right? But you could have delta ij plus a tensor which depends upon angles. And in fact, you could have local energy if you have other powers than R, but I'm not sure why someone would want that. But if you start with this, it's clear that the method should work at least, right? So generalizing this part will be a little more work than less obvious, but I mean, again, it's clear from the methods that this is. So from my perspective, okay, so there is, so this is all lambda equals 0, right? This is also lambda equals 0. And the last theorem here is Kerberger, because now you can ask, well, do I really need these log terms, right? Maybe, okay, the techniques are such that they produce them, but maybe they're never there, right? So if we start with data which are stationary outside a compact, there'll be no log terms. Maybe they're never there. And so Kerberg takes Einstein plus a scalar field plus a spherically symmetric metric is 1m or 2? 1? 1 is good enough? 2? Spherically symmetric. Field, scalar field, linear scalar field, right? And so he says, so he proves, so the data, he's giving the data at a null hypersurface here. And no, a null hypersurface would look like, well, let me just draw it in a more usual Penrose diagrams, which we were more used to, right? So this would be I naught, this would be I plus, I minus. So he takes data given on a characteristic hypersurface, backwards characteristic hypersurface here. Well, actually, okay, he takes Minkowski here. So in other words, Minkowskian data all the way to the surface. He takes a radiation which is compactly supported, incoming radiation. And he shows that generically there is a log term, non-zero log term. Exists a non-zero log term here. So this is square minus non-zero log square plus. Generically, right? There's a constant, an explicit constant depending upon the data. If this constant is non-zero, you're going to get log terms at square. Both in the field, both in the scalar field and in the right. Though, of course, well, on one hand, the answer is yes, because, of course, this field, even though the flux isn't going, but it's still this big backscattering, so it propagates. But, I mean, these theorems wouldn't apply for a scalar field, because, would they? Well, I don't know. I mean, the Friedrichs theorem would not apply, right? So, because the scalar field is not conformally invariant, is it? Yeah, it is covariant. Yeah, it is covariant. Okay, I don't know. I haven't thought about it. Yeah. The master scalar field is conformally covariant because R. No, it's not. No, it's not. They would need to take, maybe it would apply to a conformally covariant, maybe, but okay. So now this is in 3+1, right? This is in dimensions. So I mean, from my perspective, these theorems are just essentially close the subject. There is a clear example. It's obvious if you look at the mathematics of the problem that generic solutions will produce log terms, period. There's no way around it. Calculating whether they vanish or not and in which order is a tremendously arduous task. people have tried, and well, Juan wrote nice papers about it, but the papers have been written assume a lot of things which are not known to be true. Yeah. So you can make reasonable assumptions what happens here and then get relations. But the right theorem would be really to use exactly the Vasi, Shi, and Hinz techniques and try to use their techniques to calculate that. And I know that Piotr tried and gave up because it was just too much effort and it wasn't clear that it's worth it. I mean, there is an example which shows that logs will occur generically, physically relevant, and it's clear from the mathematics that they will occur generically. And if you're happy to work with space-time which are stationary over the compact set, there will be no log terms in dimension 3+1, and I'll tell you something more about other dimensions later. But if not, then, well, there are log terms and there's nothing very... Right, so I don't want to make any statement here. I don't know. In this generality. No. Yeah, well, but Hinz and Vasi tell you that everything is kind of conormal. So there is a specific way of understanding what it means to be polyhomogeneous at the corners, which is essentially this, but you have to make blow-ups and stuff like that. And so, yes, you know from Hinz Vasi that this is polyhomogeneous around this thing, but if you want to relate the log terms from here to log terms to here, you have to understand very carefully what's happening here and use transport equations to say how a log term from here gets transported from here. And it's such a mess that nobody's done this in detail, and I wouldn't give this to a student, which I don't hate, so. Yeah. So good. So this is, I think, the state of the art, yeah. So, yeah, so of course, what you could do is just to try to use the Hinz-Vasi method not on the harmonically reduced Einstein equations, but on the Friedrich equations. And that would probably give you some information that you don't get directly from the other one. That's correct. But you still have to face the fact that there'll be some singular fields to have in your setup, and then that you have to deal with equations which have singular coefficients and singular field solutions, and yeah. So. So there is a theorem that Leonard mentioned. He just takes this equation on, I think, on Schwarzschild. And you take initial data, which are of the form phi is equal some function of the angles at t equals 0. So at large distances, right? And r larger than 25. Phi of angles, theta phi times r to minus p, where p is a positive. Actually, he needs p larger than 1/2. And dt phi is at the same t equals 0 is some other function. And I think he probably takes p minus 1 or something like that. And he can write an explicit constant so that no log terms at scri plus is the same that this function phi 0 is a constant of p times this function phi 1. Okay. So if you fine-tune, well, in the interior doesn't matter because it's by domain of dependence. So if you fine-tune your data for this wave equation, then you will have no log terms. If they're not fine-tuned, you will. Okay, so this is an example of a theorem which tells you more information. How useful that is? Well, at least it's explicit, but it's again an indication that, well, solutions will be polyhomogeneous and general. And why would one only assume such initial data? So take p equal 1, take p equal 5, right? Because 1, maybe you say, well, it's not going to have finite energy. So take p equal 25, decays very fast. If these terms are not exactly proportional to each other, with a specific constant, you'll get the log term. Well, from the point of view of geometry of geodesics, this is a very nice, this is the right picture, right? Because this is the endpoints of null geodesics. But so if that's the only thing you care about, then you forget this one. From the point of PDEs, this is the picture which allows you to prove things. Let me just say that this part actually has already been introduced by Beig and Schmidt. To understand the structure of the gravitational field at large distances without going to scri. So that's not new. But they never used it to prove things, but they noticed that this is something which shows up naturally in the equations. Then it has been used by Ashtekar in something called the SPI framework. And then it's used by Prabhu and friends in a very nice paper, which says if we assume a lot of things about this structure, then something is true. But they do assume a lot of things about the whole space-time, which, yes, are true, certainly, in this case. But in other cases, who knows whether how large is this set of space-time which satisfies their assumptions. Right. And I'm putting, this has to be put, if you look at the equations, when you add this Beig-Schmidt boundary, or actually Friedrich called this I0, this Friedrich boundary, then there is a singularity at this point. And one way to, they're using a framework invented by Melrose, which says whenever you have a singularity, you make a blow up. And it works in many situations. I don't know a meta theorem in mathematics which tells this works always, but it works in this case too, right? So because you have a singularity when scri plus meets I naught, you have to blow up this point, and then you do analysis on a manifold which has an extra piece of boundary and an extra corners. Well, it's all singular, but it is singular in a controllable way. So for example, when you work with operators like that, right? Or these functions are, if you take x to be pi over x to pi over half, right? Then you differentiate it, pi is about 3. So this is 1 something. So it's differentiable, but as long as, well, but it's not twice differentiable, right? So when you want to work with functions like that, you can work with operators which look like that. But there are some more singular blow-ups that you have to do where this is a little more complicated, where you need to put different powers and something like that. And so it's a fact of life that it works for many equations in many situations, including Einstein equations in the vacuum. Right. So you could be perverse and try to take an initial data surface, which is like that, and I don't know. Okay, but if you take a hyperboloid or a characteristic surface or a standard space-like surface, you're good. And then, but yeah, so maybe that's a very perverse question. Okay. So you could take something like that, right? Yeah, I mean, you can't do, probably you can't do, I don't know if you can find a space like one like that, but maybe, yeah. Okay. You could be here, right? Right, because you're saying that, of course, there could be, is it possible? Could there be photoregions without a black hole? Because we like to think about photospheres around, right? R equal 3m, or there is a fat region in Kerr. A priori, there's no reason why there shouldn't be, right? But of course, now the metric is not going to be stationary if it's not a Kerr. So you could think that maybe this region will actually evaporate, so somehow disappear, right? Well, okay, but I mean, yeah, that's certainly something which might be important for this kind of consideration. Well, they're all written down in the Hinch-Lassie paper. But what you do each time you have a place like that, you introduce new polar coordinates. Right? So let's see how if you have, for example, let's see how can one understand this. Well, anyway, yeah. So that's the idea. Introduce new polar coordinates around every point, which seems to be in which the equation is singular. And then this gives you new coordinates to work with, and then you get evolution equation in these new coordinates. And the clever thing is just to use what are polar coordinates, right? So either you can just use if you are on the plane, then either you can just use polar coordinates, or if you are in the upper region, you use y and y over x, right? Y over x will be an angle. So in this region, right? So one way of introducing the polar coordinates is just to make projective coordinates out of your. So that's often most simplest for the equations. So good. So, but the talk was about how to do this, maybe, and I will not explain how to do this, but let me just put some history behind this, because, well, in some sense, for me, this kills the subject. But it took many years and many work just to somehow people trying to do this before they killed the subject. So I can tell you what's been happening. In particular, lambda equals 0. The theorems don't apply with lambda equals 0, right? So I'm sure that techniques could be used again, but I can certainly tell you a few things about what happens if lambda is different from 0. This definition is coordinate invariant. Because you make a smooth change of coordinates here. And that's why I didn't want these functions to depend upon the boundary. Because now if you make, that's going to, you can just, anything smooth can be absorbed here. So if you make a new function x which vanishes at the boundary, then you can write it as a smooth function. Okay, so I mean, this is all in the category where you have a boundary and you know what are the allowed coordinates near the boundary, then any new coordinate in the boundary can be written like that. Then if you replace your x, maybe you do it the other way around, right? You replace your x by this one, then x to the power s will, this one will, and this you absorb in your coefficient. So that this is invariant. And you have logs, well, you know, log of a product and so forth. So once you have the equation, you can just know the right. So how do, whether this structure is enough, I think it just, you sit down and you find, right? I mean, it could be the case you still have to blow up these points or something like that, right? Okay, yeah, so that's a good point. And so certainly at scri, there is one log which is, let me go through the history of this. So some history now. The basic paper is Penrose 62. He assumes a smooth scri also some high regularity. And then he gets some asymptotic expansions for the metric, and that's something that many of you know, and I hope I have them. There's how many of them? 3 or 4? 4. Okay, thanks. And this one is or r minus 1, right? Actually behaves like r minus 1, is it right? And this one behaves like now the other way around. Which one is which one? This is. That's scri class. This one is 5. Okay. Okay, minus 4, minus 3, minus 2, minus 1. Okay, so this is Penrose, and he assumes that you have a smooth scri, but at the time nobody knew that there is a single space-time except Minkowski that has this property. There was an almost example were the Robinson-Trautmann metrics, but they were not known to exist. In that Robinson-Trautmann wrote down an ansatz for a metric, reduced the whole problem to an equation, and one single equation for a scalar function. And if this scalar function exists and has smooth solutions, then you get an example. Right? But at the time, this was not known. So now this Robinson-Trautmann equation is well understood. And we know that the Robinson-Trautmann were actually a good example. With a smooth scri, everything was happening. Now, there is a paper by Couch and Torrance, and I think that's the first one that I know on this. Is it 72, maybe something, 10 years later? Let me cross-check the date, but, they show you that, well, they just redo, yeah, it's 72. They redo essentially the whole analysis, but assuming something less, and they show that you can get a consistent picture in here with r minus 2 minus epsilon here, same minus 2 minus epsilon, r minus 1, r minus 2, r minus 2 minus epsilon. Okay. So you can consistently solve what I would call now the characteristic constraint equations in this setting. So let me just now put some mathematics to this. Rather than assuming there is a space-time, you can work on a null hypersurface, right? So you can just do this. So this is lambda equals 0, and you do the characteristic Cauchy problem. So I'm finally coming to the title of the topic, which is in the title of my talk. So let me remind you how this works. A good way to understand the characteristic Cauchy problem, well, there are two of them. One is just you take two characteristic hypersurfaces which intersect transversally. So if you maybe want to think of this as, well, this would be in 2 dimensions, but you could just multiply this by something, right? Or you could also think about a light cone from a point, and this would be a characteristic hypersurface. And then in this case, there are some nice coordinates which you can attach to every one of these surfaces, the Heisenberg-Moncrief coordinates, and that's easy to understand what the characteristic constraints are about. And so the way you write the metric is G is minus alpha du plus dr plus u. Let me take my notes. I don't want to write something wrong. So this one I'm sure is like that. And yes, okay, good. U alpha du, okay, plus u beta plus dr. Still doesn't work. Okay, I think something, okay, good. I think that's GAB, XAB. Okay, good. So we'll see if this works. So if you look at the surface u equals 0, then this goes away because there's a u in front. This goes away because there's a u in front. Well, du goes away anyway. I mean, there are u's in front, but I'm just, let me cross-check this because I just, doesn't feel right. Yeah, so that's dr here. Dr, okay, that was, this is good, dr, okay. Good, that's good. So u in front, u in front, u dr here, okay? So if you look at u equal 0, well, du goes away. This goes away, this goes away. So you have your dropping signature, right? So this is a characteristic surface. So if r is constant, then this is 0. So the whole thing drops away. So r equal constant, r characteristic hypersurfaces. So that's the coordinate system. And the Randall's theorem is that you give GAB on N1 and N2. You give beta on the intersection. There is a constraint, which is Raychaudhuri equation on each surface plus Raychaudhuri. So this is almost the best of the world, right? Because these things are almost arbitrary. And the Deutsch-Aduri equation mixes alpha and GLB, and it reads d theta over dr minus alpha theta. The sign is plus sigma square plus in vacuum in any dimensions. That's the propagation equation for theta, which is theta is let's say well, there's a symmetric version of each, so say on n1, say theta on n1. This would be GAB, dr GAB, and I think there's probably a 1/2 here, or something like that. Not quite sure about this. So this is the, if you remember that these are no hypersurfaces, this is the expansion scalar of these hypersurfaces. Okay, so this is, and sigma, right? So sigma is a trace-free part of dGAB over dr. So you have to give yourself, so GAB is arbitrary, GAB and is arbitrary, but except for this condition, right? Well, okay, GAB and alpha are given on the surface, and beta is given only here. And so, and with this, you get a solution of the equations to the future. And there are various versions of this theorem, but so let's say that the state of the art would be that you get a neighborhood like that. So, so this is two intersecting surfaces. And on a cone, well, actually, you still, light cone is the same, but you don't have the second surface. You only get a regularity conditions here, right? So to get a regular metric, you need to impose some regularity condition. Then you have only one surface, and you're giving this G and alpha. You certainly can, but I mean, I don't know how to construct them. I mean, well, that's generally, I mean, just take Schwarzschild, right? Take a point on the singularity. Right? Then, so you can make, yeah, so you can certainly, right? So this is R equals 0 in Schwarzschild in the Macron, and you're going to get one. But if you want, maybe you want a smooth one at the tip, right? And then you get a regularity condition. So you get a well-posed evolution problem here. And note that if you are familiar with the Rayleigh-Durry equation, you probably don't have this term, because this term can be set to 0 if you take an affine parameter here. So if you take an affine, if your coordinate r is an affine parameter, then this alpha is actually 0. You can just check this, and you get the more familiar form of the Rayleigh-Durry equation. But there is no reason for this parameter to be affine. If you're using boundary coordinates, then you'll have this formula as well. But alpha will not be affine, actually, will be whatever it is. Now, what is also nice here is that if theta is non-zero, then you can algebraically solve this equation for alpha. So whenever you have a null surface which has non-zero theta, then then GAB is arbitrary, and you solve this equation for alpha, and that's your data. So it's really much nicer than the usual space-like Cauchy problem when you have serious equations to worry about. This equation on expanding cones is very, very pleasant. Right? So this is the characteristic Cauchy problem, and then all this analysis here. So For a cone, what would be the existence theorem? Well, I think that the state of the art would be, well, that if you give, you save data on the light cone, which are smooth here, and I can perhaps say a little more about this later, then you get a neighborhood of the cone in the first go. And if the data are close to Minkowskian, you're probably going to get, but I don't think it's written down anyway, that if the data here are close to Minkowskian, you're going to get a global solution in the future, but I think it's likely. Yeah. Good. So if you think in terms of the Cauchy problem, then this, I've made it formulated like that. It's very easy because you have something completely free to give, but you still have a lot of Einstein equations. So you have to build these things are free, and from these things you build your remaining metric functions. And so, for example, this Couch-Torrance analysis is making some assumptions about how G behaves. You can work yourself up through a ladder of hierarchy of equations and get this kind of behavior, right? Formally. But this is all at the level of the initial data. But now you have to solve the Cauchy problem and show that there is an evolution which goes with it. And that's this requires more work. So that's the work that Hinch and Fuzzy are doing. You can do this with a cosmological constant as well. This Cauchy problem, this theorem is the same. The Raychaudhuri equation doesn't change because if you have matter fields, what you're going to have here is this actually RR. So the Ricci tensor on the null direction. So adding a cosmological constant doesn't change this because dr is a null tangent. So a cosmological constant will still give 0 here. So you have the same thing. And if you want to get evolution, so for example, if lambda equals 0, and you are in n is so n is, let's see, I never said what n is. So n is the space dimension, right? So this is space dimension. So if n plus 1 is even, right? N plus 1 even, I think it's correct. Yes. Then the analog of the Corvino-Friedrich holds, analog of the Corvino-Friedrich holds. So in other words, you can say more. If you have data which are stationary outside of a compact set, you're going to get a smooth scri in these dimensions. But if n plus 1 is odd, then you get a PAG expansion with 1 over, in terms of half integers powers, right? In terms of half integer. Yeah. Right. So, and so this is this uses this abstraction tensor techniques of Michael Anderson, and I'm not going to explain how you do this, but so whether or not you get a smooth solution is not known. But what is known is that you're going to get a solution which is polyhomogeneous with half integer coefficients in the solution, right? So that's going to be an expansion with not 1 over R, but 1 over R, 1/2, and so forth. And yeah, one could then again try to characterize these things in more detail, but maybe that's not worth the effort. Good. So what happens with lambda when lambda is non-zero? So lambda could be both positive or negative, right? So let me just remind you shortly some theorems of. Yes. No, so here I'm really talking about. Good. I'm sorry. I probably changed tack a little bit. So this is. Yeah, I should have said that here before. I mean, it has nothing to do in principle with this expansion, with the characteristic Cauchy problem. I mean, it's true with the characteristic Cauchy problem as well, but it's already true before. That I forgot to say that. Okay, so I'm sorry if this is confusing. So this, yeah. As I said, Hinz and Vasi assumed n equals 3, and then you have to start thinking what happens in other dimension and so forth. And then if n plus 1 is even, you have a version of Kovino-Friedrich, so smooth scri no log terms. But if n plus 1 is odd, you expect that this is sharp, that there'll be 1 half integer powers in the expansion. Maybe there's a miracle again, which says that there are no log terms, or that the coefficients in front of the half integer powers are 0, but that's a different story. So good. So now, so what my point was the following: that one way is to understand results a la Penrose or Couch torrents is assume that there is a space-time which has some property and work it out. But another one is actually look at the characteristic initial data, and you're going to get this expansion at the level of the initial data. So then this is a statement without further hypothesis. Who knows whether there is space-time? Who knows how it's going to be behaved? But you can certainly set up a consistent framework where things like that behave at these characteristic surfaces. So that's why these expansions, new scri should be looked at just a good way of looking at the expansion in scri is just to look at think in terms of characteristic hypersurfaces. How much time do I have? I'm probably gone over time already. I started at. Okay. Well, let me tell you two more things maybe about what you can do with this light cone Cauchy problem. Because first I like it. I find it cool, and then I should erase this. And then you can actually prove a scattering problem, right? So. So how do you, what is the existence theorem for light cones? So you want to give data on a light cone, you want to get a solution to the future. How do you write your data here? Of course, the data are still these fields that I wrote here, but the question of regularity, in particular smoothness, is very tricky to express when you're giving a tensor in spherical coordinates. So how do you capture the fact that a metric written like that in spherical coordinates is smooth? And there are two ways of doing this. The first one would be the following. You give yourself any metric, take any metric, G0, say, calculate its light cone, right? So go into normal coordinates. And then G0, so you get a light cone, which is like the Minkowski light cone. In normal coordinates, the light cone is just exactly the surface x0 is equal x. And then you can read off, well, you can perhaps parameterize use the affine parameter on the geodesics, x, and then read off GAB from B0. Right? Okay, so this will not be good because at this stage you're not satisfying the Raychaudhuri equation, but then use this equation. Now, if you are on a light cone, the expansion of the generators behaves like 1/r near the tip. So certainly is non-zero. So you can use this equation to solve, to satisfy the calculate alpha. And from the Raychaudhuri equation. And this gives you, and the theorem is there exists a smooth Einstein metric in the interior with this data. Okay. Which satisfies this data. So you're avoiding the problem of saying what it means for a metric GAB to be smooth. Well, it has to come from some smooth metric. And so this gives you solutions to the future of this point. Now, interesting solutions can be obtained if you move this point to I minus. So question is, can you make give initial data on scri minus viewed as a light cone of I minus? Can you get a solution of the equations out of this? And the answer is yes. But the procedure for finding the data is slightly different. Rather than doing this, you can do, well, what is the free field, right? The free field is the ingoing radiation field, right? So an ingoing radiation field would be some component of the Weil tensor. So what you have to do instead is just to give some components of the Weil tensor on your light cone. And you want to make sure that that's regular enough, consistent with the conformal framework. One thing to keep in mind is the following. Suppose you had a smooth solution of this problem in a set like that, and you can extend your solution a little beyond and use Friedrich's equations to get a smooth solution backwards. This means that the Weil tensor here will actually have specific property because Friedrich, in his conformal equations, one of the variables is the Weil tensor divided by the conformal factor. And the conformal factor for a light cone would be actually eta alpha beta, x alpha, x beta. So if you want to have a solution of this problem, which has nice properties conformally, then the Weil tensor divided by this function, which vanishes quadratically here, should be 0. The Weil tensor has to vanish at scri, that's the part of the peeling story, because the conformal factor vanishes to order 1 here, but here you get an extra power. So then the theorem for this light cone at I minus is that you take any metric, right? So the first step is before. Then what you do is calculate its Weil tensor. So suppose I didn't go all the way to I minus, then what I would do is just calculate the component, so that would be psi 4 or something like that. So Y tensor C alpha beta gamma delta contracted with the normals on the light cone. And the claim is that there is a solution of the Wattmann-Einstein equation which has this data. Right? So exists a solution for a finite cone. Well, for a cone in space-time. Now, if you want to push this all the way to scri minus, then if C alpha beta gamma delta and gamma and delta divided by omega square is smooth, then you get a solution where this is I minus. Get a scattering metric. At I minus. Yeah. At the origin, right? So, I mean, the only problem is omega equals 0. Well, I mean, so this should be smooth, right? So it has, so the Y tensor of this metric is to vanish to order 2. And of course, has to vanish to order 1 here, because that's the radiation field. The radiation field is this divided by omega. So you have a well-posed Cauchy problem for space-times, which is smooth scri. And now, of course, if you want to go beyond I0, then you can switch on VASI and say that then you're going to get polyhomogeneous solutions to the future. But in this way, at least you get a neighborhood of scri minus. I think it's probably I've already gone over time, so happy to answer questions. But